hodgepodge of some different geometric topics. We're going to work on our understanding of linear measures, the metric system, conversion of units, dimension analysis, perimeter circumference, and we're going to begin to look at ratios for similar figures. The English system is going to be a system we tend to measure in yards, foot or feet, and then miles. This is the equivalence that we use, and then it's equivalent to 1 yard is 3 feet, 1 foot is 12 inches, and then 1 mile is 1,760 yards or 5,280 feet. So to convert units of measure, we have to first reference that chart and figure out, okay, well, how many yards are in a mile? How many feet are in a mile that I can then convert to yards? Once I get that conversion factor, I can then begin to translate it. And it should make sense that if I'm looking at converting miles to feet, the number of feet should be far greater than the number of miles. And then when we convert to yards, it should also be a slightly smaller number because of the conversion ratio. If I'm using dimensional analysis, then I'm looking at different dimensions that can convert one unit to another. So it works with what we call unit ratios. So that would be how I utilize this using a unit ratio approach, which I find for most students, this is the easier method for them because we tell them the denominator should always be the same unit as the original item here. So I have to make sure they're constantly canceling out across the top and the bottom with the units. It's a little bit easier to see it that way. Here's an example problem where I'm going to take the 60 miles per hour the cheetah travels, and I'm going to convert that to feet per second using that unit analysis method. And it's really nice because you can cross out on the board and show them the different conversion factors as they change. The metric system has some symbols and prefixes that are commonly used with them. We don't tend to talk about things in reference to a kilometer or a centimeter, but we tend to use that in science. So while it's not in our everyday vernacular, some of these units are required in order to use formulas your students will have to be able to utilize in their science classroom. So if I'm looking at benchmarks for metric units, this is the type of question where you're asking your students, does a gallon of milk make sense? Is a gallon an appropriate way to measure? And we're trying to teach them how to visualize things. So if I'm trying to teach them how to visualize things, I can have them hold their arm out and I can tell them that a rough estimate of a meter would be from the opposite shoulder to the tip of their fingers. Obviously, it's not going to quite be accurate because they're much smaller than we are, but that gives them a baseline visual property. And then as we're converting, this step diagram is really helpful to draw on the board to help your students understand the relationship between the different prefixes. So if I want to convert to the following using those prefixes, I'm going to use multiplication and division by powers of 10. So if I want to go from kilometers to meters, using that graph I had before, a kilometer is 10 to the third. So if I want to go to meters, I'm going to take that and I'm going to multiply that by 10 to the third. And I'm going to follow the same process for the other parts. Now, if I want to use distance properties, the distance between any 2 points has to be positive. We can't travel -5 blocks. We have to have a positive quantity. And then at the same time, if the distance is equal, we can say the distance is, for instance, the distance walking to school and walking from school is the same. That's what AB equals BA means. We're just moving in different directions on the line. And then we know that for any 3 point, there's some distance between B and C is greater than or equal to the distance between A and C. So meaning that I can put C in different places on the diagram and relate it to both A and B. Now, the triangle inequality is an often underutilized theorem to help students understand if a triangle can be made. So I can't just throw out 3 measurements and create a triangle with those 3 random measurements. It has to meet the criteria that the sum of the 2 smaller sides has to be greater than the distance of the third side. So when we ask students a lot in standardized testing, they'll say things like, can a triangle be made with these sides? we are doing the triangle theorem. So because 15 plus 18 is not greater than 37, that doesn't form a triangle. Now, the distance around a plane figure is known as perimeter. So that's the idea. I take all the sides of the figure and I add them together, and that gives me the perimeter. So in these examples, if I was going to find the perimeter of each of the shapes, I would add 3, 3, and 3. I would add L plus W plus W. So perimeter can be done either with variables or with whole numbers. Here's another example. So what you're noticing is, as I'm doing the perimeter of the variable, if all the sides are equal, then it's the number of sides times the value for each side. And remember, when we say a regular n-gon, regular figures have the same length for every side. Now let's look at circumference of a circle. Circumference is the distance traveled around the circle. So imagine if I cut a string that's in a circle and I laid it out flat, it's like a perimeter. So the circumference is the same idea as a perimeter. Pi is the ratio between the circumference and the length of its diameter. But for most of our students, we're going to tell them to approximate that at 3.14 at this stage in the math game. So then if I want to have arc length, I can take that idea of 2 pi r and I can divide it by the portion of the triangle. So that's why I'm going to do that theta divided by 180, because I'm giving the portion of that circle that I'm looking at. Here are a couple examples. Find the circumference of a circle with radius 2. So I'm going to plug in 2 times pi times my radius, which gives me 4 pi. If I know the circumference and I set it equal to solve for the radius, I would get 15 pi equals 2 pi r. I would divide both sides by 2 pi to get 7.5. This time I have an arc of a circle. When I have the arc of the circle, I'm going to use that arc length with the angle divided by 180, and then I'm going to simplify. Then if I want the radius of an arc, I'm going to use that same formula with the theta over 180, pi times r, and I'm going to plug in to solve for the arc length.